Should we start?
Yep.
Some greetings. I'm hoping everybody got something to eat there and everybody registered. Yeah. Logistics-wise, you probably passed the bathrooms when you came over, so backtrack your way if you wanted to go back there. I think my job was to really start the meeting, which is called the meeting to order. And I think Radha is going to introduce. Take from the next and then on.
Hello everyone. Thank you all for joining us. I have a few announcements that I'd like to make. Firstly, thank you all, and I want to thank Dr. Bhaskar for joining us in such a short notice. I think 2 months back I met him in Lawrence, Livermore, and he said he'd love to come here and speak with us. And he specifically picked this topic because he thinks a lot of people in our area would be interested in this. Before I go further, first I want to thank our sponsor, AMD, for letting us use the venue. And we need more sponsors. Though our chapter have enough money to run for a couple of meetings, I think it's kind of going in a negative slope. So I'd like to know if any of you can suggest some other sponsors, or if you can get some sponsorship from your company, that would be great. Right? We do run with volunteers. We have 5 volunteers here today who's been actively pursuing to get the meetings going on. But we need 1 volunteer specifically for this time going forward, is whoever can raise money. That's very important to us. And please do register on our website. You can probably, since you guys registered it, it's not a big issue. And we have a lot of meetings coming up. We pretty much booked till end of this year. And as you can see, in the September, we have Professor John Boone coming from UC Davis. He's going to talk specifically about the CT scan, the system challenges from signal processing, image processing, all the challenges that he had. It's going to be a wonderful talk. And then 24th, we have David Starr from Rambus. He's going to come and talk to us about the information theory, signal processing challenges in the small computational video camera. And then October 8th, we haven't finalized on the topic yet, but John Treichler, he has agreed to come and speak to us. I'm hoping it's going to be a pretty interesting topic, since he's going to be speaking on that. And November 12th, we have Gaussian Prior from Microsoft. He's going to come and talk about their, Cortana and personal digital assistant technologies. And December 10th, we have Andrew Singer. He's going to come. He's our distinguished lecturer. He's going to come and talk to us from signal processing entrepreneurship. And that's pretty much what I have. With that, I want to hand over the control to Vijay to introduce our speaker.
So I'd like to welcome Dr. Rao. I'm going to do a highly compressed and lossy introduction of him, because when I saw him on Google, it was like so much to say about him, and I figured that it's probably better that you guys read it there and listen to his talk rather than me spending time telling him what he does. And I mean, he's an IEEE fellow and also a distinguished lecturer, and he's a prolific and celebrated author and participates in so many meetings. Time is really an issue with him, but I'm glad that he was able to spare time and come to speak with us tonight all the way from UC California. I mean UC California, San Diego. Sorry, not Davis, San Diego. A couple of other things about Dr. Rao. He's on the editorial board of Journal of European Association of Signal Processing. Dr. Rao received his BTech from IIT Kharagpur, India, and MS and PhD from University of Southern California in 1983. And since then, he's a professor of electrical and computer engineering at San Diego, where he holds the Ericsson Endowed Chair for Wireless Access Networks, and he is also the director of Center of Wireless Communications. Welcome, Dr. Rao. Please enlighten us with your new topic. I feel so little standing in front of you with all the knowledge, so I'll just step aside.
Good evening. I know this is a little late, so I appreciate all of you coming at this time of the day. Can you hear me? Yeah. I do want to thank Vijay for the introduction, and also for Radha for inviting me here. I'm also here to raise money. No, I'm sorry. What else can you do in Silicon Valley? I said, I must raise money. And Radha said that, oh, he was asking for money. I said, what? I thought he was going to give me money. So maybe I came to the wrong place. So what I wanted to do was, I'm going to talk about, as a professor, I'm always eager to share what we are doing. But I thought what I would do is, it's not clear everybody is very an expert in this topic. So I would spend some time trying to motivate, to give you a broad outline of what the main issues are and why it's exciting, okay? And then probably delve into something that is more related to what we do at UCSD. Of course, feel free to stop me anytime. I'm happy to answer questions. There's no need to wait till the end for a question and answer session. To start, of course, I need to thank my students. The work that I am talking about is bits and pieces of several students. So my students, David Witt, 3 of them already graduated, okay? But this is the prerogative of a faculty member. He continues to work even after they left. So they continue the work, and so I will be talking about some of the pieces of the work that they have done. Okay. So let me start by motivation. This is really my motivation, but hopefully it will also motivate you for this topic. Right? First, I think it is an area with many potential applications. Right? And this is one of the things why I like to go and talk about this, because personally I'm a theoretician, okay? And I know there's a big difference between theory and practice. There's still a long way to go before it becomes useful. But certainly, I think being aware of the tools maybe will excite people to try and apply them. I think in general, even if you're not interested in this problem, the tools that I'll talk about I think should be of interest in general. Okay? So as a signal processing theory person, I always, whenever someone comes with me and gives me a problem, I always ask, does it fall under some problem that I already know? Okay, so I look into my bag of tricks and see if one of them works. Okay? And the richer your tool set, the more likely you'll find the right tool. Okay, so I think this is one useful tool. More importantly, I think in the last 10 years, some very interesting results have come out that make this field a little more theoretically sound and comprehensive. Okay? And so it's pretty timely. So we can say we have some guarantees. So if you are into guarantees, there are some guarantees available. As a result, this is a good theoretical area. I will take a slightly different tack to this problem, which is I will take a Bayesian approach to this problem. So, and I will try to connect to the other techniques when I get to the right place. Okay? But my view would be starting from a probabilistic viewpoint and then saying, how do we address these problems? Okay? And I will try to articulate why I think that is a good idea. Okay? All right. So this is the outline of my talk. So I will first define the problem for you, what it is. Okay? And then I will talk about some extensions. There is a vanilla version, and then of course nothing in life will be like the vanilla version. Okay? But you draw some insights, hopefully that will help you with with the more general problem that you care about. But I think there are some interesting extensions I want to also share. That way you can see that it's not limiting. Okay? That way you feel like, okay, maybe I can figure out ways in which I can broaden this area. Okay? And then, of course, I want to spend a few minutes on applications. Okay? And I want to touch upon them just simply to alert you to what areas people are working on, and also to show how you can revisit old problems with new tools. Okay? So it's my favorite hobby of mine. I say, let me go back and look at all the old problems that I solved and see if I can actually solve them with this. Does this new tool help me? Okay? And I would like to articulate the answer is yes. Okay? There are cases where we were using tools that were not appropriate because we did not know the right tool. Okay? And so in my mind, this provides you one new set. And then I will talk a little about some of these Bayesian methods. Okay? I will talk about two classes of methods. One is the maximum posterior methods, map methods, and then I'll talk about empirical Bayes. Okay? I realize the audience may be more applied, so what I will try to do is maybe not the details, but why and how and where the benefits are likely to come from. I will try to stress that, but I'm happy to delve into the theory if there are questions. And then, of course, I will try to conclude. So let's start with the problem definition. Okay? By the way, the first time I saw this problem, I said, must have been solved. And this was 20 years ago. Okay? One of my grad students came to me with this problem because she went to Los Alamos and she worked on a summer internship and she came back with this problem. Okay? And I said, it must have been solved. 6 months later, I was convinced it was not solved. Okay? So, what is the problem? As you can see, it's a linear system equation that we want to solve. Okay? And we have n measurements. This matrix phi is known. We usually assume phi is known. Y is the measurements, and we're trying to solve for x. Okay? And what is typical about this problem is there are many more unknowns than there are equations. That's the unique part of it. Typically, when we look at these problems like least squares, we have fewer unknowns, more measurements. Okay? So that's a typical least square setting, where you have fewer unknowns and more equations, and you try to do a least squares fit. Here you have more unknowns than measurements, and you're trying to solve for x. And from a basic linear algebra, we know, let's ignore noise for the time being. Okay? Even if there is no noise, we know there are infinite solutions to this system of equations, assuming some reasonable conditions on phi. Okay? So the question is, how do we solve this system equation? We have to put some constraints on x. Okay? Once you constrain the space, hopefully you can resolve this ambiguity. Okay? And the constraint here is that x has mostly zeros. Okay? Only a few non-zero entries, and but you don't know where they are, and you don't know what the size is. Okay? All we know is that there are a small number of non-zero entries in x that satisfy the system equations. Okay? And that's really what this problem is about. The sparse signal recovery is about trying to extract a signal x with a small number of measurements, with the knowledge that x is sparse, mostly
phi known.
Pardon?
Is phi?
Phi is known. Okay? Phi is known. Okay? And I'll say a little more about phi and where it could come from, and how maybe phi may arise in applications.
Are the values in x correlated in any fashion?
That would be the extensions. Okay? So if you had to go to the extensions, then that's where we would go. Okay?
Do you mean non-zero or do you mean positive?
Non-zero. Non-zero. Positivity could be put in, but that would be another constraint. Okay? The more constrained the space is, the better the chances of solving it. Okay? And that's one of the things I would like to stress. I think that sometimes the theory is not enough, but in applications, we have a lot more prior knowledge, which we may not be able to exactly state mathematically. But when you give me the solution, I can tell you it's useless. Okay? Because it doesn't satisfy some physical constraints, it doesn't have any physical meaning. Okay? So you look at the answer, you say this is not a reasonable answer, purely based on the knowledge that you have about the domain. Okay? So there may be ways in which you can actually constrain the set in practical applications. Okay? So I would like to actually, even though theoretical guarantees are good, I think we want to maybe not be obsessed about theoretical guarantees, but see if it applies. Is this problem formulation meaningful for the application at hand? And how do we solve this? So what is the problem statement? Mathematically, it's easy to state. Okay? We want to count the number of non-zero entries. This is what's called the indicative function. It just is 1 when the entry is non-zero and 0 when the entry is 0. So we simply count the number of non-zero entries, and we want to solve for this subject to this system equation in the no noise case. Okay? The extension, when there's noise, of course you allow for modeling error. So you say I want to still count the number of non-zero entries, and I want to allow for some fitting error, okay, modeling error. So first, let's talk a little about extensions, because I think already a question was raised about correlation. One is block sparsity, where entries are not necessarily single points, but blocks. Okay, so you'll have sparsity, but each entry will be a small block of non-zero entries. And I'll talk a little about where maybe this can take place. Okay. Multiple measurements, I will just talk about one measurement vector, but you could get a sequence of measurements, and you may be wanting to solve something like this over a sequence of measurements. So you can imagine an array of sensors. You're making measurement from an array of sensors, and you get multiple measurement vectors, and you're trying to solve them. Okay. Of course, you can combine these two, where you combine block sparsity with multiple measurement vectors, and then time-varying sparsity if you're looking at as an evolution over time. Okay. But I will focus mostly on the simple problem, and then hopefully you can see ways in which these Bayesian methods will extend, which is where I think the power of the Bayesian methods are. When you change the problem a little, there may be a very, very methodical way in which you can extend the tools. Okay, so here's block sparsity, where entries now, there are a block of non-zero entries and a small number of blocks that are non-zero, fall in the same problem. And there are many variations on that. The blocks are equal, blocks are unequal, you know the block boundaries, and you may not know the block boundaries. So there are all these variations one can imagine in this problem. Okay. Multiple measurement vectors, now instead of having one vector of measurements, you have L vectors. Okay. And what you have is that the non-zero entries occupy the same position, the same location. The amplitudes may change, but they're evolving over time. Okay. So now you, instead of having non-zero entries, you have non-zero rows. Okay. So you want to solve the system equation with the constraint that you have a small number of non-zero rows to satisfy this system equation. So let me spend a few words on applications, and then I will talk about how we go about solving these problems. Okay. There are actually a whole lot. In fact, if you look at the last 5 years, everybody who's heard about this area have begun to find ways in which to apply these tools. So there's a proliferation of applications. How well they're doing, I cannot vouch for them, but I will say that some areas have shown promise. Okay? For instance, you know, the early work was by Malat and Kaufman and Donahoe on signal representation. Okay? This one is actually easy to understand. If you think about it, let's suppose there is a particular transform you like, okay? And then suddenly you find that for a certain class of signals, another transform is better. Okay? You want to use both the transforms. Once you glue the two together, you get this phi matrix, which is much bigger than the number of measurements you have. So it's no longer square. You've now gone to a skinny matrix. Okay? So you can imagine this phi matrix being multiple transforms just simply concatenated, and you're trying to figure out which transform is appropriate for the signal at hand. Okay? And you let the algorithm decide. Okay? This is the problem of EEG and MEG. This is the problem that actually got me started on this problem. Okay, this is where you have a number of sensors on the head, and you're trying to understand the activity in the brain. Okay? And I will elaborate on that later. Okay? Now it turns out you can apply these ideas for robust linear regression and outlier detection, and this will be a problem probably of quite interest to a lot of people. If you have data, and there's data there, some data is less reliable than the others, you're not sure which one has outliers, and how do you prune this space? Okay? Speech coding. I bring this up because people in speech coding have been working on this problem for a long time, actually, in the 80s, but they never called it. It was just hidden in the applications, and only people who are working in speech coding knew about it. Okay? So in a way, this area has been there, and if you dig hard enough, you will find them hidden in some paper. Somebody has worked on it for that particular application. But the theory is not accessible. So if you have to really go and understand what they did, you would not get past the jargon. Okay? You would be stuck at the jargon level and not be able to identify what the true problem is. Okay? So in that sense, actually this problem has been revisited in many places. Okay? But I would say they did not have the theoretical guarantees we have now. Okay? And they did not have the understanding we have now. So that's probably fair to say. Okay? Of course, this whole thing was got to a big boost with compressed sensing. And I will talk a little about what this problem is when I have a chance. Okay? MRI shows considerable promise. Okay, I know the group at Stanford and Berkeley have been looking at MRI and how to apply these techniques for imaging applications. Okay? Any place where measurements are expensive, this is a good idea because you want a small number of measurements to do your problem. Okay? In wireless channels, where you have a channel with a large delay spread, but with small multipath, this would be another place where you would apply. Okay? Most people probably would just truncate. Okay? So maybe that's one simple solution to this problem, but may not be the best thing to do. Okay? And I know then there are groups applying this to face recognition and cognitive ratings, okay? Where you're looking for holes in the spectrum. Okay? You can imagine a large bandwidth, mostly unoccupied, and you're trying to figure out where the holes are, and you try to solve a problem of this kind. And the list grows. Okay, so all you have to do is look at some of the conferences, and you'll see people applying them to many application domains. So I will spend a few minutes more just to make this a little more concrete, so that when I get to the mathematical part, hopefully it'll be bearable. Okay. So here's the MEG problem. Okay. We have sensors on the head, okay, and we're trying to figure out activity in the brain. Okay. And we would like to get a very high resolution image of the activity in the brain. Okay. That means the number of sensors you can place on the scalp is limited. Okay. So you have a limited number of measurements you can get. Okay. And yet you would like a high resolution image, okay, from these measurements. Okay. So you want high spatial resolution, and how do you do this with a small number of measurements? What we do know, and at least that for a particular stimulus, certain parts of the brain are active. Not the whole brain doesn't fire up. It's a very efficient machine. So only small portions of the brain will be active, and so we know when we reconstruct the image, there should be certain areas of the brain that are active and the rest is not active, or at least dominant. So this is really indicated by this kind of picture. And you can see that block sparsity would make immediate sense here, where you would imagine regions in the brain being active rather than points in the brain. If you divide up the brain into voxels, small areas being active as opposed to single voxels. And the forward model comes from the physics. Okay? Here the phi would come from the physics of the problem, where you would say, if I had a dipole at a certain location, what would I see on the scale? Okay? And you would simply come up with a model for this through the physics. Okay? So phi would come from the physics. Okay? In many applications, phi would come from the physics. In some applications, you get to choose them. Okay? It depends on the problem. Here's a case of channel estimation. I'm assuming there are people here in the wireless area. So if you have a channel where there are a few taps that are non-zero, you're trying to do equalization, or you're trying to do channel estimation as part of your receiver design. You have a large number of coefficients, but you know many of them are zero. You just simply don't know where the multipath is. And for instance, as you know, in CDMA, people have been talking about 3 fingers, 6 fingers. That means there's a certain number of multipath, and there's a limited amount of multipath. Okay? But the delay spread can be large. Okay? And this is particularly true for underwater acoustics. Okay? This has been true that underwater acoustics, you get bounces, and they can have a very large delay spread. So you could start off with a channel with 100 taps, and maybe only 10 of them are non-zero. You just simply have no idea where they are. Okay? And you would like to use this information in your estimation process. Okay? And just simply to make sure you realize the advantage, if you're trying to estimate 100 coefficients, okay, the variance will be proportional to the number of coefficients you're estimating. If I told you which 10 are non-zero, this is a gene-aided system, and I told you only 10 are non-zero in this location, your variance will go down by a factor of 10. Okay? So it pays to go and know where they are. Okay? So if you pay an overhead in finding out where they are, then you can reduce the variance. So there is a benefit to be had. Also, from a physical point of view, it makes sense, particularly if you're drawing inferences. The location may have meaning. Like in the brain, it's not just you want to know what X is, the location gives you significance about the activity in the brain, so it has physical meaning. Okay? In some cases, there's no physics. Okay? You just want a small number of coefficients. Okay? They may have no interpretation, but in some areas you may be able to interpret the result in some meaningful way. I want to visit the speech modeling. This is a case where people did not have these tools. Okay? And many of you may be familiar with LPC, and they would minimize the minimum true norm, the mean squared error at the output to find the coefficients. For many years, people knew it was not the right model, particularly for voice speech, where you have a glottal pulse exciting the vocal tract. The glottal pulses are periodic and they are sparse. Okay? They are not a continuous excitation. So when you have the signal, the speech signal, and you're trying to reconstruct the model, you have this information for voice speech, which is about 2/3 of speech, that the excitation is actually sparse. Okay? So you could revisit the speech modeling all over again with these tools, okay? And you'll be pleasantly surprised with the results you get. Okay? I cannot give this talk without talking about compressive sensing. Okay? So I do want to touch upon this, but I do also want to distinguish between compressive sensing and the sparse signal recovery problem. Because I think the sparse signal recovery problem is very general. You have systemic measurements, and you're trying to find a vector that is sparse. Okay? Here, this problem is you create a problem where this arises. Okay? So it's a very specific instance of sparse signal recovery, okay? But very clever. Okay? So what is the problem? Okay? And this is, I will use the examples people in compressive sensing use to motivate this. Here, B is an image. Okay? So imagine you are compressing an image, and psi is your favorite transform. Okay? And all goal of all transforms is that in the transform space, you have a small number of non-zero entries, or at least a few large entries, and the rest are small, so you can throw them away, and you can just simply transmit the non-zero entries. Okay? So this is behind DCT, all these transforms tend to use this. So the question is, if you are only interested in a small number of coefficients, it says that B lies in a small dimensional space, because there are a small number of coefficients that explain B. Okay? So why bother to collect B in the first place? Okay? Why not collect a small number of measurements and reconstruct B with a small number of measurements? Okay? And that's the idea behind compressive sensing. Okay? And let's try to understand this a little better, because this is really a very interesting change of paradigm when it comes to compression. If you work in the area of compression, you'll realize encoders are very complex. Decoders are extremely simple. You spend all your energy in trying to come up with the best compression scale. Look at a video compression scale. A lot of the energy is in the compression, in the encoding, because you're trying to find the best way to encode the signal. The receiver is very simple. Okay? This changes the paradigm completely differently. It says, I'm going to give you a very simple encoder, make the life of the receiver very difficult. The decoding will become very difficult. But this is a perfectly good, depending on what you have. Okay? If you have simple sensors and a strong access point where you can do lots of work, then you want your sensors to not be doing all the hard work. So you may want to reverse this paradigm. So this is a case where I think this is a discussion I remember having 20 years ago, because base station, you want your handset to be simple. And yet you tend to do all the hard work in your handset, and the base station which receives does very little work. Okay? So I say you need to have this asymmetry, you want to be able to switch it. Okay? So this is the idea behind this. So the question is, what do we do? Okay? And here's the idea. Do not collect B, which is your image, but collect some linear combinations of B, which is Y. So you have your image, you create a system that only collects some simple linear transformations of B. So you transmit Y, you never transmit B. And you don't do anything at all at the encoder. You just simply do this linear transformation and you ship it away. Okay. So the receiver now has access to Y, has access to A, because it knows what the transmitter did, and it has access to psi, because this is the transform that we're trying to use. So it knows A psi, so it knows phi. And X is what you want to solve. So you now can solve phi times X equal to Y with the constraint that X be sparse. Here, though, you have a choice of A. Okay, so you get to choose A. So if you choose A carefully, And there's a lot of nice results. This is where the theory has gone a long way. Okay? What are good A's to choose to make this problem happen? So what have we done here? So we solve for x from y, phi x equal to 1. And this is again a sparse signal recovery problem. You have a small number of measurements, a vector that you're trying to solve that has many non-zero entries, a small number of non-zero entries. Once you have x, you can get b back by just psi times x. So you can reconstruct b as psi times x. Right? So you have now really made, so all the hard work is being done at the receiver, not at the transmitter. And you can imagine maybe from storage point of view, you may not want to store B, you may not want to store Y, but there are things you can do, and there are many ways in which people have begun to use this idea. Okay? But people have used the idea of compressive sensing too generously, I think. Okay? They may have no A to choose, and yet they'll use the word compressive sensing. Okay? In that case, it is not compressive sensing. Okay? If you're trying to solve this problem and phi comes from nature, then you're not doing compressive sensing. Okay? You're solving a sparse signal recovery problem.
So will you say something about how to choose A?
I will not. I think I will assume.
You might want to choose A such that the columns of big phi are of further as possible.
Yes, yes. So the simplest answer I would give is IID Gaussian. Okay, zero mean IID Gaussian is one where these are called what are called the restricted isometric property, RIP condition, for which recovery results are given. Certainly, if you lose rank and so on, you will not. But even then, you have to prove that you preserve this property. Okay? So I will comment on some of them as I get to the algorithms a little, but I would like to, there's a whole slew of work in that context. So there is no shortage for you to find information there. Okay? So I feel I would like to bias you in a different direction. Okay? Because I think too much energy has been spent in that direction, and I would like to steer people in a slightly different direction. Okay? So I will say a little less on that, on the typical what I call L1 recovery techniques, and spend more time on a little different set of techniques. And I will again try to distinguish and clarify what the differences are. Okay? Okay. So the issue is you need to recover a sparse signal X, and then you need to design A. So when you talk about compressive sensing, you need actually to design one more extra work to be done, how to design the sampling window A. Okay? Any questions out there? I know it's late and people are tired, okay, but I will be happy to get feedback. Open loop is not good. Okay? So you think everybody is following and your data rates may go too high. Okay? So I do want to slow down and give an option to ask questions. Okay.
Is the term compressive sampling and the term compressive sensing synonymous, or is there a difference?
No, I think at least for me there's no difference. Yeah, yeah. So. Okay. I do want to revisit one more old problem. Okay, this is just to show you that you can go back and actually solve many old problems with this new tool and maybe get better results. Okay? Here's an example of people know, for instance, this is a least squares problem now. Okay? We're trying to solve y equal to xc plus n. We have many more measurements, so there's no sparsity issue here at all. Okay? But the thing here is the noise is not Gaussian. We know if you do least squares, it's optimal when the noise is Gaussian. So we try to minimize y minus xc, the norm, 2 norm squared, and we solve for the least squares problem. The typical assumption we know, and also it's known, that if the noise has outliers, okay, then the least squares estimate is very poor. Okay? It's very sensitive to outliers. Okay? And there are robust techniques that have been designed. It's not like this field has not been studied. Okay? But what I want to show you is these tools can be readily used, and they may give you a new option for the same problem. So what we do is we say, okay, the noise has outliers, then I can split it up into two components. One is the traditional Gaussian component, and the other one is the sparse outliers. By definition, outliers better be sparse. If you told me there are too many of them, then I say they're not outliers anymore. Okay? You either need to get better equipment or do better experiments. Okay? But at some point, the number of non-zero entries in W must be small. Okay? So now again, you see sparsity in W. So you can actually combine the C, which is the unknown, with W into a new vector, where phi is just I, and then try to apply these recovery techniques for this. Okay? So what will happen is you put now a constraint on W that it be sparse. Okay? So the same tools can be applied At the end of it, you will actually get to know which noise samples are large, are actually outliers, and you can either throw them out or weight them properly in this process. I think now I'm ready to talk about algorithms. Okay? So why is this interesting? It turns out if you want to solve for this problem optimally, this is known to be NP-hard, okay? Exponential complexity. You would be choosing, you have n unknowns, and you're choosing k non-zero entries, n choose k. Okay? So for any realistic problem, this will explode in complexity. So if you do an exhaustive search, not practical. Okay? So you would not be there, you would not be able to do it in an efficient manner. Okay? As a result, this is good for academics. It means there's a whole possibility of plethora of techniques you can ask, you can develop, and then study what their properties are. Okay? And there's a whole class of techniques. I will simply elaborate on I will talk in detail about the last class, the Bayesian methods. The first is the greedy search techniques. Okay? These are what are called the matching pursuit, orthogonal matching pursuit, and there's a whole variety of that. They tend to try to search for these columns in phi one by one. They say which is the largest, look for one non-zero entry first. Once you identify one entry, then you go out to the second one, and then you try to sequentially identify these entries. Okay? And once you see one, you can come up with your own. Okay? So it's one, oh, you're late, too late. Okay? You know, if you were doing this 20 years ago, you could probably have a name attached to one of these algorithms. Okay? But now probably all combinations have been tried, all kinds of combinations. But essentially the idea is to look for, do a greedy search. Pretend there's only one non-zero entry and ask which one it is. Okay? It's easy because it just requires search of them. Then you go out to the next one and so on. The next class is people who like to do optimization. We want to minimize this using some gradient techniques and so on. But unfortunately the indicator function is not continuous. It's either on or off. Okay? If x goes from 0 to epsilon, it goes from 0 to 1. Okay? So this function is not continuous, so simple tools like gradient-based techniques will not work. Okay? So what you need to do, and which is what people do, you need to cheat, which is change the cost function. Okay? You define different cost functions, okay, which hopefully still reflect the old problem. Okay? And this is where a great amount of progress has been made. Okay? You relax this problem, and L1 minimization is the most popular. You minimize the L1 norm of the solution, and then you use optimization techniques to find an answer. Okay? Of course, the challenge is trying to show that what you're doing is solving the original problem. Okay?
Is that equivalent to calculus of variations in some sense?
No.
Where you introduce auxiliary variables and then you do minimization, both against the original variables and the auxiliary variables.
I'm not sure that's the case here. Here you're relaxing the cost function. Here what you do is you change the cost function, which is more tractable. So it's a relaxation of the cost function to get to a point which is tractable, and then you show that the new cost function you have still has some connection to the old one. So it's more a convex relaxation of the cost function. And then the last set of techniques are these Bayesian methods, where you actually start with putting a prior on x, and then you try to use a Bayesian technique to solve for x. Okay? The difference between these two techniques is really in how you relax. Okay? So if I give you a new problem and I say, give me a new recipe, you may require someone much smarter to be helping you, okay? Because the extensions are not obvious. Like the question that was asked, suppose the entries are correlated, okay? There's some structure. How do you put that structure? Okay? That means you need to modify your cost function appropriately, and that will require some kind of creativity. Okay? In the Bayesian method, sometimes you can ask the same question, but there may be a more principled way in which you can put this structure in. Okay? And so when you're faced with more general problems, you may be able to incorporate that much more readily. Okay? And you may want to try this, by the way. Like, for instance, the row sparsity that I talked about. I say, what would be the L1 equivalent of the row sparsity? Okay. And I'll leave you with the Bayesian techniques without telling you how to do the multiple measurement. And ask you, what is the Bayesian equivalent? And you may be able to figure out which one is easier to extrapolate, okay? And so on. Okay. So the Bayesian techniques basically are based on putting some kind of prior on x, and then using this prior to come and resolve the ambiguity. Okay, that's the main idea. So there are two classes of techniques I will talk about. One is the map, and the other one is the hierarchical Bayesian estimation techniques. These techniques are actually quite general, but I will talk about them in this specific context. But the message is, these ideas could permeate other applications. Before I go into details, first I want to spend a few minutes trying to distinguish the two, so that you can see what is the difference between these two before I use it. Okay. So I want to make sure you can see that there is a difference between these two, and what is the flexibility you go from one to the other. Okay, and then I'll talk about how exactly you implement these techniques. Okay. In map estimation, you start X is our unknown, okay, and Y is our measurements. So you put a prior on X. Okay, so you say I have some underlying distribution for X. Okay. Based on the measurement, you're now trying to figure out what X is. And the standard technique is to look at the posterior distribution. You know the prior distribution, P of X. Okay, so you assume something, and you have to ask, what is that? Okay. And what you ask for, what is your distribution after you observe P of X given Y? Hopefully the measurements have reduced the entropy in your data, in your variables, and you have much more clarity. So you look for the maximum of this posterior distribution. So P of X given Y. So, and that's the map estimate. So what you do is, if you just apply Bayes' rule, you'll be looking at P of Y given X and P of X. P of Y given X is governed by the noise you assume. Okay, so this is by the noise in the model. Right? P of X is what you have to assume. Right? This is where you have to be creative. Right? So if you're given a problem, here you say, instead of asking how do I relax the cost function, you ask what is the right prior I should assume on X so that I can get a reasonable solution.
Do you need to make an assumption? Is it possible that these priors can be derived somewhere else downstream? Let's say in a communication system, the decoder may give you priors to the detector.
Okay. So the answer to this question is okay. So that's why I said application-wise, you may be able to come up with these priors. So the answer to this question is, but still you have to come up with these priors somewhere. Okay. You can make them based on the physics of the problem, or based on the data collection problem. You collect data beforehand and you can come up with a prior. But there are many ways in which you can actually do this.
But there is no limitation in the tools that it has to be Laplacian.
Oh, no. I use the Laplacian because this will connect to the L1. Okay. I just simply mentioned the Laplacian. So if you assume a prior that P of X is Laplacian, okay, and that P of Y given X is Gaussian, or the noise is Gaussian, then you get to the familiar Lasso framework of the L1. So if you were looking at the compressed sensing literature, you will see a lot of work on Lasso and L1. Okay? And in the Bayesian context, it would amount to saying I'm assuming a Laplacian prior on P of X. Yes?
So far, there is no sparsity involved in this formulation, right?
Oh, good question. Okay. So
you have to express sparsity as a prior.
Yes, right. So now I would like to, maybe this is a good question, because I think there is a balance between what you want and what you can solve. Okay? So what you have to do is constantly ask, what do I want to solve? What do I know to solve? And what do I want to solve? And try to find the right mix. Okay? This we know how to solve. Okay? And then you look at the answer, and if you're happy, then you don't ask, you go home happy. Okay? So I will ask you to be a pragmatist ultimately at the end, which is to ask, did it solve the problem I want? Okay? And ultimately it'll come down to looking at this cost function and asking what are its properties. Okay? So you can actually completely forget where you came from, and at the end, you're doing an optimization problem. Okay? You can look at the underlying optimization problem and ask, what are the properties of this cost function I'm optimizing? Okay? If you're happy with the properties of that function, then you're done. Okay? So I think I feel the Bayesian is an excuse, okay? But hopefully it'll get you to where you want to go, close enough that you may be able to say.
But is it fair to say that you have to construct the prior in such a way that it will express your notion of sparsity?
Right. So it's an iterative process. So this is with all work, we do this linear presentation. Nothing is this way. Nothing was derived this way. Nobody sat down one day and said, this is how we're going to do it. There were many iterations, and then they decided to tell you a story which is very clean. Okay? So in that sense, this is not clearly yes, it is. You will cheat. You'll go back, look at what you got, and say, oh, I don't quite like it. Then you change it, and you go back and say, what kind of prior will be reflective of this, and you play games. And I will shed some light on that. Okay? So it's not completely backwards. So this is the hierarchical relation. What you do is you introduce one more layer of random variables gamma, which control these x's. Okay, so you use a hierarchical framework, and these gammas are random variables with their own prior, okay? And they're connected to this, so you have a Markov chain. Okay? And one can ask, are we complicating the problem? Yes and no. Okay. If you add too many layers, yes. If you add enough layers, it's not true. Okay. And it turns out this is probably one more maybe, but this is where probably you get the most bang for the buck. Okay. And what you do is now you pretend you actually solve for gammas. Okay. So you pretend the x's are nuisance variables, and you actually solve for the x's, for the gammas. So you solve the same problem. Now you do a map, but you solve for gamma hat, which is the same thing. Okay. You look for the posterior distribution of gamma given y, and you solve for this. Okay. The nice thing about this is then at the end you can actually get a posterior distribution, P of x given y, if you do it correctly. As I said, I'm going to give you a high level just to show you why we're doing what we're doing. Okay? Because the map estimate only gives you a point estimate, doesn't give you the posterior. Okay? It's very hard to calculate actually a true posterior. This one, if you do this carefully with this hierarchical framework, you can get a true posterior approximation of P of x given y. If you care for the peak, you can go for the peak, but you actually have the actual distribution of the estimate. It turns out the Laplacian can actually be done this way. You can actually write the Laplacian in terms of a Gaussian and a P gamma, which is a Laplacian, an exponential. And I will elaborate on this more. But what I want to point out, you can actually treat the Laplacian in this hierarchical framework, where x given gamma is Gaussian, and P gamma itself is an exponential. So you can revisit the same Laplacian in this hierarchical framework and redo the problem. Actually, it's been done. So it's called Bayesian lasso. So if you're looking at L1, I say please go look at Bayesian lasso first. You know, I think these things are a little better, have better properties. So the message here is that you could start with the prior and go down the map path. And I'll talk a little more about that. Or you can use a hierarchical framework and actually go after the an approximation to the posterior and have a little more flexibility. Okay? Complexity-wise, the approach is not too bad. Okay? So I would like to argue, if something works, then you worry about complexity. Okay? So as an academic, when my students come to me and say, it's too complex, I say, does it work? Okay, if it works, then I would worry about complexity. Okay? So in my mind, the tools, I will show you some simple toy problem, because on real data, it's very hard to know what is the truth. Okay? So I will have toy problems for you on where we know the ground truth, and then we'll just simply try to see if the algorithms can actually reveal the truth to us. Okay, so let's go to these map techniques. Is anybody keeping track of time?
Yeah, we have 25 minutes.
What time do we end, rather?
We have 25 more minutes.
Okay, I think, yeah. My objective is to get your curiosity in mind. Okay, if you go back and look at this work, I'm very happy. Okay. So what I would like to do is I'm not really worried about the details, because at some point you would have to go back and look at the literature.
Dr. Bhaskar, just one question. Can everybody hear? The microphone is not working, but I think he's speaking loud enough that we could all hear.
Hello?
I can hear you, but I just want to hear all.
Yeah, I was telling him I teach in a room bigger than this. I have more students, so I am used to it. So it's not a problem.
We'll get some more water.
Yeah, I just want to get some water.
If you walk to the middle, to solve it at the level of the physical matrices against the encoding matrix, if you walk to the middle of the room, you'll be closer on average and in worst case.
Yeah. By the way, my dad was a physicist. Now, when I told him what I did, he said, you're doing poor experiments. We should design better experiments. Okay? Which is analogous to your question. Solve the problem by doing the right thing. Okay? So let's look at what the options here are. Okay. We are interested in solving for x hat. Sorry. The only thing we need to really choose in this case is P of x. And that's the only flexibility we have. Okay? And there are many options you can try to promote sparsity. I think as Boris pointed out, Laplacian by itself is not really sparse prior. Okay? Because if I ask you to generate a Laplacian variable on your computer, you never generate 0. Okay? You can generate 1,000 times on the computer and you'll never get a 0. Okay? And yet people refer to it as sparse prior. Okay? It turns out what we'll show is these densities have bigger tails compared to the Gaussian. So they're likely to generate larger non-zero entries, and that's what helps you. So we will go towards densities that have higher tails. Okay? So I'll talk about this in a minute. Okay? So, and it turns out there are many growing options for solving the underlying optimization, which is the good news. Because people like the L1. The reason people like L1 is because it's convex optimization. You could go to Stanford, download a toolbox, and within 2 hours you're running, you can actually do compressor sensing. You have a very nice way of running L1 programs, and so you're off and running. Okay? So that's the convenience of going through convex optimization. Okay? But what I would like to maybe leave you today with is there are actually many more options available for even solving these problems if you set them up right. Okay? So once you're finished with the L1, if you're happy, then you're done, of course. If you're not happy, then there are options. Okay? And of course, you can always relate to the lasso by saying, look, choose the Laplacian prior, and you have it. Okay? So let's look at what we're doing here. Let's take a few more steps. So usually we take the log of this, and so it splits into a sum. If the noise is Gaussian, then it's a quadratic function, and log of px translates to this g of x. There's nothing complex here if you assume Gaussian noise. So all your work is in figuring out what properties of G will actually give me sparse results. So this is the question of how do you choose your prior. Okay? This is the underlying optimization problem. You want to make sure this gives you sparse results. That means it is a clever choice of G, which means a clever choice of P. Okay? So you can backtrack if you wish. You can start both ways. Okay? And here's the result that actually tells you how to choose a sparse prior. If G is non-decreasing and strictly concave function for x in the positive octet, we only care about x greater than or equal to 0. G is a scalar function. For x greater than or equal to 0, it needs to be a concave function and increasing. Once you have that, you can claim that the local minima of this optimization problem will be extreme points. That means we'll have at most n non-zero entries. Remember the vector is M, capital M long, and it will have at most n non-zero entries. Let me try and put this in context. This is what was known about L1 till 10 years ago. So if you go back to the literature 10 years ago and before, this was why people used L1. Because linear programming, and we know from linear programming that the optimum solutions are at these extreme points, and that you will have at most n non-zero. Okay. That was what motivated people to do L1 for a long time without the guarantees. What this says is you don't need to do L1 as long as you choose your G to be a strictly concave function, a non-decreasing concave function, you will actually be able to guarantee this. That gives you a whole slew of priors you can select. Okay. So let me start with a few priors and maybe walk you through. This is the Gaussian prior. This is no for sparsity. So the Gaussian prior is completely not a useful prior if you want sparse entries. This is like, in a way, when you put a Gaussian prior, you're asking for a very democratic process. Everybody participates. So you will get lots of entries, non-zero entries, everybody contributing little to explain the data. Right? So it is a very democratic process, and you will get everybody will be non-zero. Okay? But you're not interested in democracy here. You want a few winners and everybody else to be losers. So you want few non-zero entries and the rest to be zero. Right? By the way, if you try this Gaussian prior on the brain, the whole brain is lit up every time. Okay? So if you try to do this inverse by using the L2, you will find for every excitation, the whole brain is reacting to it, which we know is not true. And here's the Laplacian prior, which will give you the L1. Right? And this is the transition. People realize this is bad news. This is good news because it gives you sparse results. This is, by the way, this is neither convex nor concave. It's just on the boundary. Okay? So for optimization purposes, you call it convex. For sparsity purposes, you call it concave. Okay? So you just change the story depending on what is it that you want to convey. This is right on the boundary, so you have just gotten to the point where you can get the benefit of both worlds. Let me say a few more words here. Because people do this all the time without knowing, and I want to just re-emphasize it, because this is, like for instance, many of you probably apply the FFT. When you're given a signal, you do an FFT. And you look at the spectrum and you draw inferences from the spectrum. And there are many people who complain the FFT does not have enough resolution. I think this is common, complaint about the FFT. So let's take a simple example. Let's suppose I gave you 100 samples, okay? And I said, give me the FFT. Most of my students will take a 1024-point FFT. Yet the data is only 100. You have 100 samples, you took a 1024-point FFT. Okay? It is exactly the old problem. You have 1024 unknowns that you're trying to solve from 100 measurements. Then you can ask, what problem did I solve? Okay. It turns out you're actually solving this problem. And we know this is not going to give you high resolution. Okay. It will spread out, there will be a smearing effect, we have all this language we use to explain. But it is really, if you go back to the system equations, you are solving for 1024 unknowns with only 100 measurements. Okay? And your phi matrix is these exponentials, all the harmonics you're trying to use for fitting it. So next time you take the FFT, we want to do something different. Okay? So I just want to split it because this is really almost like everybody does the FFT, and then sometimes they want more resolution on a small number of samples. You can't get it. Okay? I suggest use the L1 at least, okay? And you will see surprisingly good results. So what are the sparse distributions? One simple class is to go to x to the p. Instead of p being 2, p less than 2. P2 is a Gaussian, so you choose a p which is 1 will be Laplacian. You go below 1, you will start going toward more and more sparse priors, and P0 will be where you start counting it. So what happens when you make P 0.5? This blue curve is 0.5. You will find it will have heavier tails. And so as you make P go towards 0, it will have heavier tails. The concentration at 0 and then heavier tails. The heavier tails allow for these outliers. So, but P less than 1 is concave. So the optimization problem is not favorable. Which is why you stop at 1. Because if you really want convex optimization, 1 is where you need to stop. Okay? But we know P less than 1 will actually give you better priors. So here's an example of things that people have tried. One is log xi squared plus epsilon. This is like the Cauchy distribution. This is by Chartrand and Yin in 2008. Log of mod xi plus epsilon. This is by Candace, Boyd, and group from Stanford. And we've been looking at x to the p for p less than 1 in 99. Different choices will give rise to different levels of sparsity. So you have a prior, if you choose, you can enforce sparsity. And the question is, what is the problem? Why not just go with the one that gives you the highest prior? Okay? Remember, it's a concave function, so the minima, you have many more minima, and you'll be stuck in local minima. If only you can get to the global minima, then your problems are solved. Okay? So that's really the problem. It's the optimization problem. Even though I wrote it, I never told you how to solve it. Okay? Let's go back a little. Yeah, this problem, we know it has desired properties, but we don't really know how to get to the global minimum when we solve it. That's why we want convex optimization. So what do we do with this? I will say it is a problem and it's not a problem. Okay, so
No,
let me
if,
try.
if,
Yes.
you, if you knew the G, why can't you solve it by some mechanism?
You can solve, but you may get stuck at a local minimum. So because you see, your landscape is now full of pitfalls. You can get to, if you can get to the global minimum, you are in good shape. Okay? But any algorithm that you use, if you use some kind of gradient kind of technique, it will get stuck in the local minimum.
What does Milner need? Milner need a very old algorithm, the triangle, where you do reflection.
I think we would have solved it. Otherwise, we would not be obsessed with convex optimization. Okay. Okay. So it is a question of getting to this global minimum that is the problem. But let's try and maybe I want to alleviate this fear because in most applications you may already have an answer you like, and if your job is to simply clean the answer, remember to solve global optimization, if you start close enough, you will converge. So the question is, how do you initialize properly? So in many cases, if you already have an algorithm that you're happy with, or is giving you reasonable answers, that means you're in the ballpark. And it's just a matter of just running one or two iterations of this and cleaning it up. So what I would like to say is this, really this whole idea of provable guarantees is good, but in many applications you may be able to come up with a good guess that puts you in the ballpark, and then you need to just simply clean it up. Okay, so what are the options? Okay, so here's the dilemma that we face, and I will indicate this P. P equal to 2, not good. If the prior is too sparse, it means if you go towards 0, then you're likely to get stuck in the local minimum. And I'll call this convergence error. That means you were solving the right problem, but you just didn't get to the right answer. Okay? You got stuck in the local minimum. If the prior is not sparse enough, which is what P close to 1 is, okay, then you can converge to the global minimum, but it may not be the sparsest solution. This is what I call structural. You have a problem with the formulation because the global minimum is not your true answer. Right? So you have this dilemma between the two. Right? By the way, we have a lot of nice results now showing when L1 will converge to the true sense. Right? As long as you have enough measurements and there's a bound of the measurement that tells you can get it. Right? So this is the dilemma in this framework. How do you get to the right answer? But there are nice recipes available. Okay? So if you're looking for recipes to solve this, let me try and give you one or two. So we want to minimize this function. Okay? This is a nice quadratic function, so we will not lose sleep over this one. This is concave, and that's our headache. So there will be what I call reweighted L2, L1 algorithm that I'd like to show you that can address this problem quite nicely. And the essence is very simple. Okay? What you do is you try to bound this function by a nice concave function, a convex function. So you try to find bounds, and you minimize these bounds. Okay? And by minimizing these bounds, you actually show that you will converge at least to a good local minimum. Okay? So let me try. This is almost a very nice. This is what we do, by the way, when we do the EM algorithm. All these things are basically fall under the same class, which is majorize, minimize. What we do is, I have a picture to show you what that is. Okay? So here's an example. Here's g of theta that I want to minimize. Okay? It's a messy looking function, and not what I want to do. Here's my estimate. Okay? Instead of minimizing g of theta, at this point I create a new function that bounds this function, upper bounds this function. And I minimize f of theta. And I get my new estimate theta n. And we can show actually theta n actually also decreases g of theta. So you actually create a nice bound for this function, and then you minimize the bound, and you continue to do this. So you refine this bound. Why is this a good idea? Because this is a concave function, and we know we can actually fit a supporting hyperplane to a concave function. You can always bound a concave function with a simple linear function. We can replace it with a nice simple hyperplane, and then it will be an L1 optimization problem. So you have to run a repeated L1, because every time you get a new estimate, you need a new hyperplane, and you need to. So you get a sequence of L1 problems. So let me try and explain this with this example. Here's an example with say p equal to 0.5. This is the g of x with x with p 0.5. This is nice and concave. Remember, only thing you concentrate on the positive axis, positive side. You can, any point you can draw a line that is above this function. Okay? So if you give me a point, I can draw a line, okay? And I now replace g of x with this line in an optimization bar. And I repeat, I become an L1 optimization bar. So, and that's all there is to this. Right? We'll replace it by a line, and the slope will depend on where you, what your guess is at this point. So it will be a function of where you are, and you get a sequence of weighted L1 problems. This is a nice convex optimization problem embedded within this map problem. Many people use a reweighted L1, and I would say this works much better than the L1. So I would like you to try this. If you are a fan of the L1, please try the reweighted L1, and you may be pleasantly surprised again. But I want to point out that reweighted L1 is not a good, nothing about the L1 carries over to the reweighted L1. Okay? This is still played with the local minimum problem, all the things that go, because you're still solving the original problem, the concave optimization problem. Okay? So often people think the guarantees that are available for L1 carry over for reweighted L1. The news is not good there. Okay? Though the results are much improved. Okay? So this is, by the way, not our idea. This is actually suggested by Candice and group in 2008. Okay? For this function, they created a simple supporting hyperplane, and the weights can be calculated very easily. In other words, this reweighted problem, the weights are also very easy to calculate. Okay? So you can solve this problem in a few L1 optimization problems that you've done. Okay? Many people, if you go back and say, is this closed form? It depends on your version of closed form. Okay? So if you were born in the 60s, then only 2 norm is closed form. Okay? Anything that runs on the computer is not closed form. But for all practical purposes, this is closed form. Okay? You put it in the computer, and it gives you an answer, and you know it is a global minimum. Okay? So let me give you something that is even better than this. Okay? You can write g of xi as h of xi squared. Okay? Just change of variables. And let's suppose h is concave. Then you upper bound h as opposed to upper bound g. Then the bound will be a quadratic in the variables, because remember xi squared is what you're using as a new variable. So when you create a bound, now you have actually a quadratic operation. Okay. So you do the same trick. Okay. You replace it by a hyperplane. It's quadratic. This one you can write in closed form. It will be a sequence of reweighted L2. So your familiar L2 framework is just a reweighted L2 with the weights computed as the previous. So it's a question of whether you like this one or the previous one. I have no preference, as long as you go to the one of them. Right? But I think the L1 is too limited because you're stuck with a prior that has a limitation. Right? And it depends on having enough measurements. These techniques tend to work well. Proofs are harder to come by. Okay. So we worked on this in where this function, and again it's a very simple reweighted L2 problem. Right? The problem is these are well correct. We have nice convergence proofs and so on, but you have a problem on local minimum if you choose a P too soon. By the way, I must say, once you start seeing these techniques and you play with them, you may be able to find a way to navigate. You may want to start with less aggressive P and then decrease P gradually. So you can come, but proving will be a nightmare. So if I ask you mathematical questions, you may not be able to answer. And this is function, same thing. This is a 2. So they have come up with a reweighted L2. So there are reweighted L1, reweighted L2. There's a whole class of algorithms you can use to solve these math problems. So how well do they do? So I will show you a toy problem, okay, where you can apply this, and you know the answer, so you can actually tell which one worked better. Okay?
5 more minutes.
Really? I don't even have time. Okay, so I will. What should I do? 5 more minutes. I think I will probably end with a map and just ask you to look at the slides for the hierarchical stuff. So here, what we do is we generate a phi matrix a phi matrix is known. It's a random matrix we generate, so we know phi. Right? Then we generate x, the true solution, randomly with a small number of non-zero entries, so we know what x is. And then we generate the data as y equal to phi x. That means we know x0, we know phi, and we generate y. Then we present the y to the algorithms along with phi and ask what is x. So we know the answer, so we can check. If you got the right answer, then we know you got it correct, otherwise you don't fail. We repeat this experiment 1,000 times, and we ask what is the probability of success. Because we know they will not succeed 100% of the time, unless the number of non-zero entries is extremely small. Here are the results. This is the probability of success. This is the number of non-zero entries. As you increase the number of non-zero entries, you're going to fail more. Okay? This curve here is the L1. So if you run the standard L1 and you ask, please recover, you find it starts failing once the number of non-zero entries exceeds just about 10. This is a 50 measurements. Here is the reweighted L1. And there is your reweighted L2.
The right is better?
Right is better, because you can recover all the way up to 20 entries with this low probability of failure. The right is better. By the way, this is not, people have tried this on many data sets, and this has come out to be true. So mathematically, it's very hard to try and prove. But the justification is based on the prior. The priors are better than the L1, and they do not have this structural problem. So it's a question of getting to the global mean.
I realize in model you don't have noise.
Yes, because if you have noise, there's a reason why I'm showing simple cases. Because as soon as you complicate, how do you evaluate becomes a bigger challenge. And there is no simple way to evaluate and be sure. Yeah. Well, I can add noise and then immediately I ask you, what should I show you? And then we will not be able to reach any conclusions. Okay? So let me end with the limitations. Okay? The limitation is, of course, they have many potentially local minimum, and mathematically they could have m choose n local minimum. Okay? Imagine if m was 100 and n was 10. 100 choose 10 local minimum. You could guess. This is a very, very dangerous landscape. Okay. What I would like to then say is this is a new class of techniques which I believe are better than the reweight of the one, even though unfortunately I will not get to it, right? Because they give you one more level of robustness by going to this hierarchical thing. I'm surprised I actually gave this talk 2 months ago and I did it in 15 minutes. And the data rate is high. So the main goal here is not to seek the max, okay, but to go after the posterior distribution. And try to make sure you have actually approximate the posterior in a more efficient way. And that's what these techniques do. I want to show you something interesting before I leave, which is this is the model. This is a balance between, again, what you want to achieve and what you can achieve. So you want to set up the problem so you can actually solve this. And the key here is, how do you set up this hierarchical set model? And the answer lies in Gaussian scale mixtures. Is to represent this P of x as a mixture of Gaussians. And what that means is x given gamma is Gaussian. Okay? And then you put a prior on it. So once you give me gamma, x is a Gaussian random variable, and all you need to choose is a prior on gamma. And it turns out there are many distributions that can satisfy this. In fact, all the distributions I showed you have this representation. So you can actually put this x given gamma is Gaussian. You change p gamma, you get a new posterior, new prior. You just simply have to come up with a new way of estimating this gamma. And the beauty of this is once you condition on gamma, everything is Gaussian. And as we know, if you work with random variables, Gaussian is the best world you can live in. So once you condition on gamma, everything is Gaussian. You have nice closed form answers. Okay? So the mathematics works like a charm. Okay? So it turns out going and using these Gaussian scale mixtures is a very, very powerful recipe for addressing this complicated problem. My apologies for not being able to do this, but I thought I had more time, but I underestimated it. But this is the idea. What we will do is we will put a prior on p gamma and we'll ultimately end up with this P of x thing. And the recipes are very simple based on the EM algorithm. So let me conclude. Or let me show you one simulation result so you may be tempted to look at the
Slides will be
the slides. I will make them available. Here's an example. I won't tell you the details except to show you this is the sparse Bayesian, hierarchical Bayesian learning. This is L1. This is reweighted L1, reweighted L2. The more you go to this side, the better the results. That's what you can get with these techniques. So there is reason to go to this flavor of hierarchical Bayesian systems. Okay, so let me end. What I would like, hopefully I have convinced at least a few of you, the Bayesian approach offers an interesting and useful option to this problem. It's possible. For instance, if I ask you, I want to put correlation. You know, in random variables, we naturally think of correlation. We know how to put correlation into a random variables. So we can model this very nicely. If we have correlation in time, we can model that equally well. So the Bayesian framework, we don't need to think too much in order to add more structure into the problems. I do want to, even though I did not have a chance, I would say if you are working with L1 techniques, you may want to try it with reweighted L2. And once you are unhappy there, you may want to go to the Sparse version. Okay? If you can't there, then I say, give me some money and I'll tell you what to do. I think they're versatile and they can be easily deployed. And we have had a lot of success. So I must say, we've gone to problems which are much more complicated, and my students have been able to extend them very easily. It turns out this is not a challenge. Proving guarantees is difficult. But coming up with recipes, testing them whether they work, is not very difficult. Proving is not necessarily very difficult, it's not important necessarily if you can initialize them. So the problem really becomes, how do I initialize these algorithms? And this is the last word which I want to say is, at the end you want to look at the objective function and ask, is the objective function, does it have the desired properties? Be a pragmatist. It doesn't matter how you got there, okay? At the end, it must have the desired properties to solve the problem. So I would say all those will ultimately justify by looking at the underlying cost function and asking what are the properties of the objective function. All right, I think let's stop here.
Before Q&A, I just want to give Bhaskar a small certificate just for his memory.
Oh, I can hang on my wall.
Yeah.
Thank you. The nice thing about these awards, we place them high enough, nobody knows what it is. Yeah, I'd be happy to answer some questions.
I have a question.
Sure.
First of all, I want to thank you for a very nice talk. The second thing, I don't have very much money, but I would like to ask for perhaps a reference, perhaps a good tutorial paper that reviews the material that was in this talk. So I can go home tonight and read it.
The answer to your question is, unfortunately, there is none. It's in the works. You know, you will find a lot in L1, which is why I haven't talked about it. But I think there's no tutorial paper, unfortunately. But I could, if you go to the website, maybe if you look at some of our recent work, you may find good references.
Okay.
That's the best I can do. But you can send me an email and maybe I can try to give you a better reference to look at.
Question. In a lot of practical applications, it would be nice to have a different fee than what you talked about. Like, it would be nice to have some sort of structure. If it could be sparse itself, if it could just for like a cost, power, whatever you think about building something. And is this something that your group has looked at, or other folks have looked at, or?
I'm assuming you're thinking in terms of these sensor networks and so on, where you want to have a fee that is sparse so that it's cheap to conduct wire.
That would be great. That's a great example of it. I mean, but there are lots.
So There are two places you can, if you have a fee that is sparse by virtue of nature providing it to you, then it should enter into your optimization. So when you do the convex optimization, you'll find the word sparsity used there, but it's really used in the context of sparse. The matrices are sparse, and they exploit this sparse structure. So there are recipes in optimization that exploit this sparsity. And so you just simply have to use the right tools. Now, if you want to design the fee with the right sparsity structure, there are some results on how much sparsity will give you these RIP conditions. But those are all usually asymptotic in nature, but they provide you some guidance, so you should be able to find some results there. Okay, wait and I'll start.
Thanks so much.